afternoon and good evening, wherever you are.
Yeah.
Okay, so I've been, so in the past, okay, let's tell you a little bit about myself. I do a lot of image processing and also recently using deep learning techniques for image processing at work, and also take part in Kaggle and various study groups. Yeah, so this was my first, and I've used neural networks and backpropagation a long time, but this is my first dive into like such a detailed level analysis of backpropagation. And I'll be honest, I did struggle. So one of the, let me, before, so I talked to Joseph too. There's just so much material in these two lectures. I have to, pick some items and then focus on it. So, of course, one of the key things in lecture 4 is backpropagation. Backpropagation taught the way, it's been taught in these 2 or 3 Stanford classes. Okay. So before I start, I made this, I think hopefully this will be helpful. I made this, do you see my browser? I made this, I made a small README note. It's basically a small repo on my GitHub, because as I went through, I found a lot of different material. Okay, and you can see the browser, right?
Yep.
Yep. Okay. So basically, so this is my set of different materials I found on Backprop, and I have some notes about what type and what level of detail they go into. So for example, for our class, we have for CS224, the winter 2019 session, backpropagation is covered in lecture 4. And for CS231, it's covered in lecture 4. And they have the same themes, but I like some of the 2017 notes a little better. I thought they were there's a little more detail, and I will show you an example. Okay, and while I was doing my review and search, I also found this other class called computer vision, which is also a Stanford class, and it's computer vision, and they also talk not only about neural networks but some other learning models, but they also cover backpropagation quite well. So that's the, if you're looking at a structured a learning material, those three are pretty good. There is MIT and Carnegie Mellon, but I haven't looked at that. And if anybody has gone through those, like the MIT course, then I'm happy to add the link here. It's basically just a GitHub repo. You can make a PR too. You can send me. Okay, so that was the structured notes for backpropagation. This is, because it's such an important topic, there are so many explanations for it, right? So there are some really good blog posts, and the 2 blog posts, one by Chris Kohler, who makes these incredible blog posts on distill.io, and he makes these really great blog posts to explain difficult concepts. He and then the other really nice blog post version is Michael Nielsen's book. It's a completely online book, and I saw even some of one of the Stanford classes links to it, and it's chapter 2 in that book. Okay. Like last week we had, Joseph was leading the, so these are still, okay, you have the structured learning here, you have these blog post version. There is a PDF called Matrix Calculus you need for deep learning, and Joseph led a great review session on this PDF, and there's a lot of mathematical detail. There are, I think we spent 6 hours altogether so far, right? And I have to watch, you have to watch this again and read that PDF again to get a fully, in-depth idea for matrix calculus. That's little more than backpropagation, but it's all the. I think Jeremy Howard and his colleague wrote that. Okay. Okay. So for me, I learn well like. There are different learning styles. So one of the ideas is this is if someone describes it to you intuitively, you can get the intuition and then move forward with it. So this I don't know if there's a YouTube channel by I think Grant. I forgot his first name. It's called 3 Blue 1 Brown, and I think this is the best neural network playlist I've seen. It's like 4 videos. He starts with neural network for computer vision and then goes into backpropagation and so on. This is excellent. And he also has Essence of Linear Algebra playlist, which is great. And I think initially he did a section on multivariable calculus and multivariable functions for Khan Academy. So these videos are so good. He only has math videos, but he has about 100 million views on altogether on all his videos. It's a very well presented material. Okay, and of course, if you are like, okay, I don't care about the theory, just show me how to use it. And how do I just use it for my work, and how do I just practically run it? There is the great one-page cheat sheet by one of the in one of the Stanford classes, where essentially what we are talking for like 3-4 hours. Yeah, he's just summarized all of that here, and you can pretty much take this algorithm and implement it in PyTorch, and it works. I have an example of that. So you can see, you can see different levels, right? They're like a very structured environment, blog post, mathematical review with our friends, some YouTube videos, and but because this topic is so important, it's presented in so many different ways. And I'll share this on channel. Okay. So let's talk about how they have represented backpropagation in lecture 4. Okay. So they start with they represent the neural network with as a graph, the neural network equations as a graph. Okay. So here we have a very simple equations for, I think it's just a 1-layer neural network. Okay. And you have X is your input. Anything along the edge is the result of the operation. Okay. And then every node is interior nodes are some operations. So here, so you start with your input X, you compute Z, which is simply W times X plus B, and W is the weight matrix. And then you have a nonlinear function F, right? So H is basically F of Z. And finally, you have S, which is U transpose H. Okay. So you have, okay, so we have represented these equations as a graph. Okay. And I'll show you why, like Joseph was saying at the beginning, this is much closer to how things are implemented. So it's important to
So Mehul, I got a question for you.
Yeah.
So I think in general, so deep learning or using the neural nets Z equals W X plus B is pretty familiar. I don't know why we're doing this multiply by U and the U transform times H. What is that achieving?
I think this is from one of the things in lecture, in the previous lecture, he had that score value for, it's actually, he just took, you remember he was doing a score for us, S, which was museums in Paris are amazing. And he showed, oh, wait, maybe there's one equation. Oh yeah, this. So, this was our network, and he's trying to keep a continuity between lecture 3 and 4. Okay, so he's just showing like if S is here, in this particular example, he cares about S, so he's just he's trying to represent the same network as a graph. But I will show you one more example from CS231 where they have a different equation, and the main theme is you can represent any neural network in this format. Okay, so whatever equation you have. And you might not have, yeah, this is not common. I agree. I think it's.
So John's question was about the S, right? The S at the end. Can you see page 3 of the notes, of the PowerPoint notes?
Yeah, so it's the S and also the the U transform. I don't know where that's come from. Yeah.
Yeah, well, U is the matrix that transforms H into a one-dimensional answer, right? I mean, it's so you multiply U. It's basically a dot product with H. See, H is a vector, right? You can see that H equals f of z, and it's laid out as a vector. And U is going to be another vector whose dot product with H is going to be equal to the score, as Mehul was saying, the score S. Right, and in the previous lecture we talked about what the score was. It was something about the score of the center, the center word of a sentence, right? So that's what S is. It's the score. It's the last layer of this neural network.
So Joseph Subhash here. So the thing is something like that. U is only there. Firstly, the dimension of U and dimension of H are same. So that if we transpose the U and multiply with H, we will get a single integer value. Is that the intention here?
I'm sorry, I didn't get your question, Subhasis.
Yes, can you hear me clearly?
Yes, more or less, yes.
Okay. Yes. So what I'm saying is that, so in that case, U and H, both of these things are, first thing is that both of them are having the same dimension. So that if we take U transpose H, it is giving us one integer value. And that integer value is of essence here. Is that the case here?
Yeah, so normally when you write vector notation, you mean a column vector, right? But
right.
So in this case, it's taking U transpose to say that we need a row vector, and H is a column vector. So and you're right, they're the same dimension, and so the dot product. So U transpose H is basically the dot product between the vectors U and H, and that's going to give you a scalar, which is the score.
Okay, understood.
Yeah, and
so we are going to use this code to come up with whether like binary case or anything like that. If it is greater than 0.5, then +1, less than 0.5, +2, something like that.
It could be, it's general. As Mehul was saying, it depends on what the last layer of your network is trying to do. In this case, we're trying to compute a score. So
right.
And that's one of the problems with these class notes, here, because there is the neural network stuff and the NLP stuff, right? So in some of the other lectures, it makes it much easier. So instead of and I think I'll show you an example once we go through this. I'll show you an example from CS231. They, instead of S, they just have the loss function. They just say, okay, we just have the L here, and we are going to back propagate. We are going to try to find how, using the chain rule, I'm just going to call this delta because I don't know how to pronounce this character. So it's like, instead of delta S by delta weight matrix.
Yes, it is actually called del.
Del. Okay, thanks. So instead of measuring how S changes with respect to W, so del S by del W, in the more general case, it's del L by del W. Okay. So I'll come to that, and let's see when I show the example from CS231, it help. Okay, so we have laid out my main takeaway is this is just one network that we had in our NLP class, but let's say you have a general neural network. You can write out all the equations and then lay it out as a graph. Okay, so then once you have that, the forward pass or forward propagation is pretty straightforward. You just go along. So here you have W comma X, then you have W into X, and then you compute your what did he call it? You compute Z here, which is W times X plus B, and so on, and you will get finally a single score, right? So that's the forward propagation. And now, so in back propagation, now we had to, we did the forward direction. Now we're going to do the backward direction. Before I, one second. Yeah, okay. So he introduces some notation here. I think I've seen this in all the 3 Stanford classes I look at. So it's good. They're pretty consistent with, how they are describing this. So let's see what this is. So there are 3. So let's say you have a single node, right? Here we are just showing the h is a function of z. So you have a single node. Um, you have something called at the node. You have del h by del z, which is and they refer to it as a local gradient. Okay, so you have a local gradient at a node. You have a upstream gradient. So that is. So there was S here, so it's del S by del H. That's the gradient coming in. And then you also have a downstream gradient, which is del S by del Z. Okay, so now since we know F, we know H, we know the relation between H and Z. So H is F of Z, so you can easily compute del H by del Z. So how does H change when Z changes? Okay, you can easily compute del S by del H. That's because you have the S. But how do you compute?
Sorry, sorry, Mehul. Are you sharing the PowerPoint notes? I'm not seeing what you're sharing. Is everybody else seeing it? Okay, I'm not sure why I'm not seeing it. Okay.
Oh.
I don't know why I can't see it.
I'm sharing slide 18.
Okay. Yeah, if you would just, if you wouldn't mind, I'm following it on my own computer, and if you wouldn't mind, just tell me what slide you're on, because for some reason I can't find the shared document. So you're on slide 18.
Yeah, okay, I can stop share and try one. Start again. Let me.
No, everybody else can see it, so that's fine. It's just me.
Yeah. Okay, so this, yeah, so here, okay, we have the local gradient, and so, okay, we have 3 terms, right? Local, I'm on slide 18. We have local gradient, upstream gradient, and downstream gradient. And what he defines here is that, see, we don't know how to compute the downstream gradient, so we can use the chain rule to just say del S by del Z is the product of the 2 gradients, is the product of the local gradient and the upstream gradient. Okay, and then I think he just says the same thing in words. So any questions in this part, because this is how we are going to go forward?
Yeah, so what would be the local gradient? I understand the gradient is kind of like changing the parameters,
right,
tweaking the parameters of weights, but what's the local versus the other gradient?
Sure. So let's say in this, okay, the general idea is H is a function of Z, right? So we just want to see, so if I, for example, if I increase Z, what happens to H, right? Or if I decrease Z by 0.1, what happens to H? If I increase Z by 0.2, what happens to H? Okay, so the gradient is just telling you the relation between H and Z, right? Like if I change Z a little bit, how does it affect H? Let me show you the next slide. It has an example with a real function and numbers. And
before you go, the local gradient, you should think of it as the derivative of the local function. That is the function that's represented in that circle. All the other derivatives, notice the upstream gradient and the downstream gradient are derivatives of the output function, the loss function, or the score in this case, right? So those 2 functions are derivatives of, they have S in the numerator, but the local gradient has this local function in the numerator.
Right.
So in general, like as John was saying, like we have Wx plus B, like the weights and biases, and then on every node we are saying the weights and biases gets tuned in as we go along, and the weights and biases are going to be on every single neuron. So now looking at from the picture of this neural net, what's the upstream, upstream gradient and how do I differentiate between the two in this case, like when I take example of Wx plus b?
Okay, let me do one thing. The way and the way even the notes are structured is we'll take a simple example first, and then we'll come to the neural network, because there, right now we are with H, like with simple like X and Y and H with simple things. But in the neural networks we come with matrices. So I'll come back to your question. Okay, with
Okay.
like how it comes to it.
Okay, thanks.
Okay.
But
so,
the short answer is that the derivative is that the information flows through the network from left to right. As you see on slide 16, you see the input X is flowing through, and all of the contributing pieces, the W and the B, all of these, you can think of the information as flowing through from left to right. And so the rightward direction is upstream, right? And the leftward direction is downstream. So if you look at any node, there's a derivative flowing into it from the left in the blue vector, and a derivative, that's the upstream, and then a derivative flowing out of it to the left, and that's the downstream. So in slide 16, the upstream gradient is ds by dh, and the downstream gradient is ds by dz. Does that make more sense?
Yeah, it does. I mean, like, and that part is understood. The values of like x, w, b, like they get tweaked. But the local gradient of f, or a local gradient of like plus or a dot, that bit is not clear to me.
Well, that's the part. Well, in F, in that node with F inside, you see there's information from Z flowing through it. Z gets operated on by F to make H. Z equals F of H. Sorry, H equals F of Z. So the local gradient is, as Mehul was saying, is the sensitivity to tweaking Z. So it's basically the derivative of H with respect to Z. That's the local gradient. Notice that the other two gradients are with respect to S, which is the final output, or the loss function, or the score in this case. But the local gradient is with respect to that local function F. It's df.
Okay.
Yeah.
I think the notes have an example. I think that will help clear it up. So I'm on slide now on. Okay. So basically on slide 20, you have downstream gradient is like Joseph explained. Like if it's coming into the node, it's the upstream gradient, and going out of the node towards the left is the downstream gradient. So downstream gradient is upstream gradient multiplied by the local gradient. So just hold on to this. And let's look at some examples. Before we go to the example, there's one more thing about, so far in the graph, we said what happens, we have only a single input coming into a node, right? We only have Z. But what happens if there are multiple inputs like W and X? And then, so if you have two inputs coming into the node, and Z is just W times X, so you have two local gradients. Okay, so the local gradients are so del Z by del W. So that is, how does Z change when W is changed, and you have how does Z change when X is changed. Okay, and again the same kind. So it's the same. So multiple inputs, multiple local gradients, and then the same flowing pattern, right? You have the upstream gradient, local gradients, and then the downstream gradients. And since you have two inputs here, you have two downstream gradients, del S by del W, and then del S by del X. So just intuitively, how if I change X a little bit, how does S change, right? How does the final score change? Or how does or in the more general case, how does the loss change, right? Okay. Okay, I like these examples because it finally helped me. It helped me a lot. Okay, and I hope I can explain it well. So my function is basically, it's a function of three variables, X, Y, and Z. And it's broken up as follows, X plus Y times max of Y comma Z. And then to compute, so to compute the values, you take specific values of, he gives specific values of X equal to 1, Y equal to 2, and Z equal to 0. Okay, so what does this look like? So now you can break this into, you can lay out the equations as this computation graph, right? Okay, So basically here are your inputs. This node, the plus node, gets 2 inputs, X and Y. Similarly, max node gets 2 inputs, Y and Z. And then there is the last node is basically the multiplication of the 3, right? I wish he had put, he put here that this is A, this is, and then this is the, yeah, you get F here. Okay, anyway, but that's minor thing. Okay, so now what he did is, he said, okay, let's, just for an example to understand it well, let's put the values. So you have X is 1, Y is 2. And see, Y is being distributed to both nodes. So Y is 2, Z is 0, right? So you basically this is the forward pass, right? So 1 plus 2, 3, blah, blah, and the max of these two is just 2. And then 3 times 2 is 6. Okay, so forward pass is very easy. Okay, now Dinesh's question about the local gradients. So if you take del A by, so in this example, if you take del A by del X, it's just 1. Del A by del Y is just 1. Okay, that's it. So the local gradient is just 1 for these two variables. The local gradient for the max is a little bit tricky. Okay, so because it's the max, so del B by, okay, yeah, so it's a function of two variables, Y and Z. So if Y is greater than Z, then del B by del Y is 1. Okay, because you always, you get B and you get Y, and then, yeah, if you just take, yeah, so you get a 1. And if Z is greater than Y, why is this? Okay, these are, is this a typo here? I didn't notice that before.
No, because it's if the Z is greater than Y, that means it's the Z, and gradient
Yeah.
of Z with respect to Z should be 1.
Mm-hmm. Oh, right. It's yeah. Okay. Yeah, I think. Yeah, I think this is an indicator function. I think this notation is an indicator.
That's right. That's right. Yeah.
Mm-hmm. Okay. I think he has a small type. This should be 1, right? Yeah. At this here.
I think it's for this specific case, right? Because you have your Y of 2 and your Z of 0.
Oh, right. Right.
So
okay.
On the right-hand side, 0 is actually smaller than Y, and that's why the derivative of B with respect to Z is 0.
Oh, thank you. Thank you. Yeah, perfect. Yep. Exactly.
Can you repeat that again?
So in this case, if you see Y is 2 and Z is 0, so that's why delta B by delta Y is 1. And because Z is less than Y, right? So the derivative, so there's, in this case, this delta B by delta, del B by del Z is 0.
Because the Z is 0.
Yeah, the Z is less than Y. Yeah, that's the.
So the first equality sign is the indicator function, and the second equality sign in each equation is evaluating that indicator function at the current value of Y or Z.
Mm-hmm. Yeah, so yeah, what we need to remember is these local gradients are with respect, with respect to these values, right? So we are also, yeah, we are substituting these gradient values to get the local gradient. So for example, if Z was 4 here, if Z was 4, then del B by del Y would be 0, and del B by del Z would be 1. Does that help?
Yeah.
Okay, let me, so this is slide 27, and similarly, this is interesting. Yeah. So now you take del F by del A, which becomes B, and in this case, B was a max, so B was 2, and del F by del B is A, which in this case was X plus Y, which is 3. Okay, so now we have computed all the local gradients, everything possible. Yep. 2 here, 2 here, and 1 here. Yep. 1, 2, 3, 4, 5. Okay. Yeah. Okay, and of course, del at the end, del F by del F is just 1. So you need that. So, okay. Now we want the downstream gradients, right? So if you remember from the previous slide, it was the downstream gradient was just the upstream gradient into the local. he switched the terms here, so that threw me off initially. But I'm like, okay, fine, it's a minor detail. So here the upstream gradient is 1. So at least now it's consistent. The upstream gradient is 1, and the local gradient here was 2. So it's 1 times 2 is 2. And similarly, as you go along this arm, it's 1 times del f by del b, which is in this case 3. So that's why it's 1 times 3. Okay. As you go forward, in this case, the upstream gradient is 3, and then the local gradient is 1. So here it's 3, and similarly upstream gradient is 3 and local gradient here is 0. So you get a 0. And the last one we have to do is upstream gradient is 2. That's this number here, and the local gradient is 1 for both cases, right? So that's the final downstream gradient. Okay, so this is yeah, okay. And then, okay, why the hell are we doing all this, right? So what this tells us is, how does f change when x is changed? So if it says the del f by del x is 2, and this is an interesting one. How does del f by del y is, because there are 2 things coming in. The gradients add, and in this, yeah, okay. So maybe the simplest example is if you see del f by del x is like, so this is telling us when x is, if you increase, I think in the lecture notes in the video he says x increases by 0.1. So you make x say 1.1, and what is the effect on f, right? That's the example he gives. Let me show you one. Okay, and yeah, this is one other notation that he adds, that in the case of y, because y was going to 2 places, right? Y was going here. He leaves out the notation. See, that's why I don't like some of these notes. You have to keep going back and forth. Yeah. Okay. So here it was x plus y, and here it was max. So because you have y is going to 2 nodes, when you do del f by del y, they just showing that the gradients add.
Mehul, this is a perfect example of the total derivative single value chain rule that Joseph went through from the notes. Mm-hmm. This is the reason, and this is the classic example of, and that's what the equation shows on this page. It's the single variable, which is y, but it's the total derivative. So you have to add all the parts from the output going back to the input, which is what we saw in the matrix calculus example. So this is just an example where there are 2 parts from y input to output. So you have to add both parts. Both
the parts, okay. And yeah, so thanks, that really helps. Yeah, so this will give you how, if y is changed, if you change y a little bit, how does f change, right? Okay, before I go to this, I want to show you one more example which I really found very helpful. It is
just one question.
Yep.
So in this slide, if we look at del y, so we can call del y as the upstream gradient, and the intermediate terms like del f, del a, and del a, del y, we can call these as the local gradient, right?
So the local gradient is always at the node. So here it was. Sorry, I didn't fully understand your question, but here the local gradients were.
So here. Yeah. Right. Here, if you see, say for example, a is x plus y. So if we take del a del x, that is going to be a local gradient.
Exactly. Yeah. So these, del a. So at this. Sorry, you're breaking up. But yeah, basically, just to at this node, these are the local gradients, and then at this node, these are the local gradients, and so and at this node, you have so each node has local gradients. Okay, just think of that.
Correct. Yes. Yeah. Yes.
Okay, there was one really nice example. I went too far. Okay, one second. Let me just. So same. The nice thing is at least they are like, you know, the two classes are consistent. And let me just show you the example that really had. I actually like the CS231 a little bit better, and I'll show you why. So the same idea, like you have a function of x, y, and z, and then instead of the max, they have just x plus y and z, right? And then again, they just put down this equation in this computation graph, and because the max is not there, this becomes a little simpler, right? Exactly what we did before. Q is x plus y, and then so the two local gradients at Q, f is qz, so two local gradients at f, and we want to find del f by del x, del f by del y. Okay, and you can work through. Yeah, they do. You know, they do it nicely. That okay, you can. We already know that del f by del z is just q, and in this case q is x plus y, so it's minus 2 plus 5, which is 3. So that's it. Okay, that's the say similarly. Yeah, he just steps through yeah, each of them, that how you would do all the upstream gradients and downstream gradients, and yeah, showing with a simple example of chain rule. I believe here it is -4 times the local gradient here is 1, so it's -4 times 1, so it's -4. Okay. Similarly, same -4 times 1 is here. Okay, so yeah, I just like this, some of these notes. That yeah, you have your local gradients, you have multiple inputs coming in, local gradients, and then yeah, the downstream gradients. And here yeah, they put instead of the s, so this is the general case, right? It's the loss. And then you can continue building your graph. So the first example was really simple, and you can do. I won't go through this, but if you know, they go through this complicated example now where f is a function of w and x, and if it's e to the power minus w0 x0 plus w1 x1 plus w2. So here are all your inputs, and I think, yeah, and same way, it's I believe this is the initial values, and you can just work. I won't step through all of it because we'll just spend too much time going through all the steps. But it's the same idea, right? Downstream gradient is a local gradient times upstream gradient, and he's just showing what is the local gradient at each place, at each node. Yeah, so for example, if you have the exponential function, your local gradient is, if your function is f of x is e of x, the gradient, the derivative of that is with respect to x is just e of x, right? So yeah, and it's nice to work it out. It's just and then the nice thing is same notation, right? Okay.
Mehul, could
yeah.
you maybe go one slide back?
Here.
One more.
One more. Okay.
So just one more that we get to the previous slide. These are just like parts of the.
I see.
Sorry.
This one, yeah.
Yeah, that one. Yeah,
okay.
Thanks for showing these resources, because I haven't seen this, and I think it's really much clearer because you show here that it's the gradients of the loss, what Joseph said before.
Mm-hmm.
So maybe just to clear up, maybe if there's still some remaining confusion around this, I think this is a really nice chart showing
mm-hmm.
this. So
yeah.
what you already have is on the right side, the upstream gradient, right? It's the gradient of the loss with respect to z.
Yes.
What you want are the downstream gradients,
mm-hmm.
Which are also the gradients of the loss with respect to x and y, which are the inputs to the function, the local function f. Mm-hmm. And in order to get those, you apply the chain rule of the local gradients, which can be computed quite easily because it's just the gradient of this local function with respect to these two inputs. Combine this with the upstream gradient, which you already have, and you already have the downstream gradients.
Right. Yeah. Oh, yeah. Yeah. Thank you. Yeah. Perfect. Yep. So yeah, we. Yep. perfect. So I think, yeah, this part, yeah, this slide was, and yeah, this is just working through the examples. And he actually, so what this is a really nice example, because eventually, you know, they broke it up nicely like this, but then they show that the part here is the when I first saw this, I didn't realize it, but then when he puts the blue box around it, you see that, oh, it's nothing but the sigmoid function. That, you know, so you can so what you know, if you have time, if you listen to the lecture by the 2017 lecture on this, so what she says is, you could do like each and every step, or in this case, you know the sigmoid function and you know the derivative, so you could, you know, like just look at the derivative of with respect to the sigmoid function. And they were showing like either way you do it, you get the same value of 0.2. Okay. Okay, yeah, and then now, okay, let me go back to our 224N notes. So both of them have, they give some, they call, one person calls it patterns and one calls it like some intuitions between of what these nodes, yeah, they called it, yeah, so in 224, the professor calls it node intuitions. And I saw a couple of places that call it this way, but basically, okay, so we looked at a couple of nodes, right? We looked at a plus node, we looked at a multiply node and a max node, and right. So, so what he's saying here is, the intuition is that the plus node distributes the upstream gradient. So, for example, the upstream gradient is 2 here. So you see, it's just distributed equally on both sides here. Okay, so it's 2 and 2 here, right? You're just distributing this upstream gradient. Okay, maybe I'll show you one more and it'll make some sense. So the max node is sort of like a router. Okay, so we have the upstream gradient is 3, and so in this case, the entire upstream gradient went only along this arm, and here you got 0, right? Because for our particular values of y and z, and this makes perfect sense, right? So suppose z was 5 and y was 2, then all this gradient would be routed along this arm, right? So it would be 3 here and 0 here. Okay, so I thought this, I haven't seen it displayed. This, I thought this was nice. So you have the plus distributes, max routes it, and then the last one was, yeah, this was also very clever, that the multiplication switches the upstream gradient. So in our example, if you remember, it was just the multiplication, right, of this was A and this was B. So it was I think yeah, this you know, like how the distribute was clear, the max was clear. I think the switch, he means that, but maybe you guys can correct me if I'm wrong, is like, you see it was 3 and 2 coming in, but when you're going you switch it to 2 and 3. I think that's why they use the term 2 and 3. Does that make sense?
Yeah.
Like this, yeah, okay. Node intuitions, and I think, yeah, both places just did the same thing. Gradient distributor, gradient router, and yeah, gradient switcher. Same equation we saw before. Okay, before I come to this part, let me let's see. Okay, then he talks about efficiency in doing this. He's saying compute, you know, like so the example he gives in the lecture is, you could compute del S by del B here, and then independently compute del S by del W. I mean, I don't know why I would, okay, maybe it's just for the example. So he says the efficient way to do this would be just compute all the gradients first. yeah, compute all the.
Yeah, I think what he's saying there is that if you compute del S by del W, for example, you have to go through all the chain rule and everything, and then you just have to do it again later on. So he's saying that what he's recommending is you compute all the local gradients and all of the upstream and downstream gradients, just like you did in the example that you went through.
Okay.
And those are all the pieces, and then you can just assemble the answer, everything you need in the answer from all those pieces using the chain rule.
If you work through, the point is that the intermediate derivatives, like for example del S by del Z, is reused in both del S by del W and del S by del B. So if you do piece by piece all the way to the end,
I see.
You would recompute the intermediate values each time. Whereas if you store and cache them, and in fact, this is where going through, for example, the Andrew Ng's course, he shows why caching as you go through the forward loop and also as you go through the backward. By caching, I mean just storing away intermediate values, you end up reusing them quite often. So you don't recompute, you just reuse.
Reuse, okay. Okay.
Yep.
Okay. Yeah, and then he, honestly, I got a little bit lost in this representation. And so he says like, if you can, he talks about laying out your, laying out your computation graph. But, it's,
this is where this is an important point to solve any of the particular problems that they assign as homework and stuff. So if you go to, if you refer to some of the notes, and I'll post the note, I sent you that note, the Kevin Clark note. That particular one shows you, and a lecture from 2017 of how best to plot the graph going back from output to input and from the loss to the inputs in order to be able to do the allocation of the derivatives to each. For example, that plotting this graph is what will tell you in more complex cases what are the paths from the input to the output. And so if there are multiple paths, then you'll need to add, just like you saw in the Y case a couple of slides back.
I see. Okay. Yeah, and the note Srinivas was referring to, he, in the in the additional reading materials, there's a whole section on gradient notes. Srinivas, this one, right? Like this section 5.
Yes.
With so they describe this entire like a one-layer neural network example, and with all the dimensions. But I don't think I can cover all of this today. Let's see, maybe if we have time, we can go through it together. Let's see. So same. Oh, it's only. Okay, maybe in the end, if we still have time, I can come back to this and we can look at section. I think Srinivas recommended section 5 to me, but if you have time, I'll definitely try. Okay, so here, he talks about, so that's one of the things, right? Like, so in general, so it's just a mention here. In general, our nets have regular layer structures, and so we use matrices and Jacobians. But this, when I started delving into this part, and there's some really nice notes. I can't. Yeah, just we will run out of time. I can just point you to where what was some of the best material. Like, so one of the part was here we. In the previous example, we were just talking about like for like X and Y as just a single variables, right? So now you say X, if X, I really like this slide because X, Y, and Z are vectors. Right? And so now you have to have a derivative of, so basically as it says here, derivative of each element of Z with respect to each element of X. Okay. So your local gradients get a little more complicated, right? And but it's building on the same theme, right? And then they show the vectorized way of doing this. So you have a 4096 dimensional input vector, and if you just had the element mice max, this some yeah, they go through yeah, the local derivative of f with respect to x. Okay, so even even this is I think it you know when you move from that the single variable was really nice, and then as you move to the vectors and the matrices, it becomes like harder and harder to follow. So the previous Stanford classes didn't have it, but the latest one has this I think this is just hard, right? Like so they have an entire section on I'll just point it sorry, they had a whole TA session of like I think almost 40 slides only on back propagation, where it is just like maybe 3 months ago, right? And yeah, it's just what we are saying. We have the general laws, and here
Mehul, this is really excellent stuff, and I wonder if you could post, these presentations on the Slack group, especially that PowerPoint one from the one from CS224N, because those diagrams are really way better than the ones in the current present. Yeah.
Okay. Yeah, I'll definitely post it, and I put a link to everything here also, but I'll post the PDFs also. Yeah.
Super.
I just got okay. Sure. And this one was, I didn't get through this because it's just 40 slides of only back propagation. And, I think one of the things somebody said in the last lecture, right? We are doing all these gradients, but you could have done a random step. You could just randomly walk around and you would still get there, but you just take longer, right? So they talk about the different approaches. And they of course the same example we saw, like with chain rule, and it's nicely worked out. There is annotated slide and non-annotated slides, blah, blah. Yeah, same thing. I think this is the same example we saw from CS231, right? And from here it gets into the gradient is basically the direction and rate of fastest increase. Blah, blah. 1 second. Look at this. So this was really nice. They compute. They tell us about like how you do it with like matrices and vectors, and go through it quite nicely here, with especially with this 2-layer neural network. Sorry. I didn't make it through all the way here. I thought but this and CS231 are the two of the like that helped me a lot. Okay. Because in the current lecture he just leaves it here, right? He doesn't go much into detail. Okay. Let's see what else we got here. He makes this point about a difference between Theano, which is not so used so more, and modern DL frameworks that we all are using, like TensorFlow or PyTorch. I didn't. So he's he was complaining, or not complaining. He was mentioning that modern. Of course, the modern DL frameworks do all the back propagation for you, but for you, but mainly leave layer node writer to hand calculate the local derivatives. I mean, I've built network. I never had to hand. I don't know what he means here. This is one thing I didn't follow. You know, why he means hand calculate, because I will show you a PyTorch example, and there's no hand calculation I'm doing there. Okay. And he, yeah, now just showing like if you were doing the backprop implementations, and now the computational graph setting makes sense, right? We represented the neural network as a computational graph, and then you just have a forward pass and then a backward pass. Okay. And he talks about, yeah, okay, so if you had a multiply gate, the forward pass is very, you could write a neural network and back propagation from scratch, right? Yeah, I don't know if someone's looked at the homework, if that's what they ask you to do. So you could have a class multiply gate, you define the forward, which is straightforward, and then you just define the backward pass for it, and then just return dx and dy. Yeah, see, it's very modular now. You are breaking up, so you would have a multiply gate, you would have a plus gate. What else? Max. Okay, there you go. Yeah, that's just since it's x times y, it's the dx is just y. Yeah, okay. You just have dx and then dy described here.
So this is where, and that last slide, that's where you have to compute the local gradients by hand. That's what he means by that.
I see. Okay. Oh, I see. Okay. If you were to write it yourself. Okay, I see. Yeah. Okay, makes sense. And then he talks about before all this modern deep learning, in the old days, they used to do this gradient checking. Yeah, and he says this technique is useful for checking if your implementation. Yeah, but okay, so that's.
Could you go to just one thing? Could you go to the previous slide, please?
Yeah.
Here, like, I think he talks about something f of x approximately equal to f of x plus s and a minus of f x minus h by 2h. So he was saying something that we need to calculate maximize and minimize. I didn't get that point. What's this equation is?
So this is just a numeric gradient of the function f, right? So suppose you wanted to numerically compute, you have, f of x, whatever your function is, you can take a very small value for h, and you're just looking at how should you describe? Yeah, what happens to like when you if you just take a
we're just calculating the slope here.
No, so right. It's if you look at it, you'll recognize that it's very similar to the definition of derivative, right?
Right.
Except normally it's not a centered derivative. This is centered on the point x, and the reason why they do it that way is because it's more numerically stable. But you can see that it's exactly equivalent to the definition of the derivative. Normally,
this is the derivative from first principles.
Yeah, it would be f of x plus h minus f of x over h. That's the way they would normally define it. But this is a centered derivative centered on x, which is more numerically stable. So this is the equivalent formulation for the derivative.
Okay, so this is like a more efficient way of calculating the derivative.
Yes, more accurate.
The point is you have calculated in the previous, when you did all the stuff that Mehul took us to, you were doing it we were doing it analytically. And in this case, he's just saying you can check your analytical values by doing numerically and check that your answer is the same. So this is a technique to check the calculation. That's why it's called gradient checking. So you calculate the gradient numerically and you check your analytical calculation to see that they're correct.
Okay.
And you would just do this for a few values. You would just spot check it. You wouldn't do it for all the values because it takes too much. It takes much more time.
I can explain this in a different way. Am I audible?
Yes.
Okay. So just consider it this way. Consider that there is an xy coordinate. Fine. Now, when we do y is equal to fx, what actually we do is that we provide a value for x, and we are interested in getting the value for y. Now, the xy coordinate is something like that. You are trying to put a particular point on this xy coordinate. Now, if you want to find what is the angle or what is the, what should I say, slope for this particular point, what do? We do y by x, because that is the tan h. By the tan h, we actually take the gradient of that particular point. So going by the same example, what derivative is basically rate of change of y with respect to x. That is the definition of a derivative. So basically, we are trying to find how much y changes when we change x. That is the theoretical definition of a derivative. So by now coming to this equation, so in that case, what we need to do is that we need to tilt x to a certain extent. Then we need to find out what is the corresponding value of y. Then we need to check what change has been made to the y with respect to what change has been made to the value of x. You just take one arbitrary point at this xy coordinate. From there, that is the x point, let's say. From there, you are first increasing the value of x by a minuscule value of h. That becomes x plus h. Corresponding y value is function of x plus h. Fine. Similarly, you are decreasing the value of x by a minuscule value, that is again h. So that becomes, the x coordinate becomes x minus h. Corresponding f value becomes, y value becomes function of x minus h. So by this whole practice, what you have landed up is, you have got two values of y and two values of x. So the upper hand is basically y2 minus y1, which is basically function of x plus h minus function of x minus h. So that is the difference, that is, you can understand as y2 minus y1. That is the numerator. Now in the denominator, going by the definition of tangent, you need to provide the change of x in the denominator. So if you write the denominator without looking at it as 2h, look at it like this way, x plus h minus within bracket x minus h. So that will give you the 2h. So the numerator is basically y2 minus y1 and the denominator is x2 minus x1. So you have taken the change of y with respect to change of x, which is the tangent at this particular point, which is by the definition of derivative, that is the derivative. So that is how we derive at this point. Don't look at the 2h that way, look at it as x plus h minus within bracket x minus h. That gives you the 2h. So the numerator is the difference of y, change of y with respect to, in the denominator, change of x. That is the, by definition, that is the derivative of y with respect to x.
And I thanks very much.
Excuse me, just a little bit of context. If people are like, if you look at any kind of numerical computation of derivatives, this is known as the Newtonian method of calculating derivatives, right? Newton-Raphson method, and there are many variations to this, which are more accurate. If you want to read up more, you can check that out.
Okay. Yeah. So okay. Thanks.
Does anybody know? Does anybody know why it says approximate though? Because what was just explained very well. Thanks for that.
You are discretizing a curve.
That's
right?
because
you are replacing a curve by a straight line, and so that straight line is a hypotenuse of a triangle, right?
Right,
So
and it also depends on the kind of arbitrary choice of h in this case.
Yes,
right?
exactly.
Yeah.
That's
To make it exact, you have to make it exact, you have to take the limit as h goes to 0.
Right.
Right. Yeah.
That.
Okay, thanks.
Thanks for that excellent discussion. That if you that really ties really well with here. So you see here, they in this PDF, you could do random search. You could have the numerical gradient, like Subhashish and I don't know the other person explained really well, and basically just what we saw there. But here they just did plus h, but there it was plus h and minus h, right? So and then the like what Joseph said, an analytical gradient, right? By if you take h to the limit, Yep.
Yes, this
Okay.
is the actual definition that should be.
Yeah. Okay, so yeah, so he says this was used in the old days. I haven't, I don't, at least I don't know if PyTorch is doing it internally, but I don't think so. He says it's not useful for like practical stuff, but just I guess to give us a context, like this is before PyTorch and TensorFlow, this is how they would check their implementation. Like, Srinivas said, you are computing it with the graph, but then you want to just do a few spot checks to make sure your computation is good. So yeah, he.
So if you take Andrew Ng's Coursera course, he takes you through that and makes you do that so that you can really understand what's going on.
Thanks. Yeah, I should put a link to Andrew Ng's course too. I didn't check his material while I was preparing. Yeah. Okay, so here he says we have mastered the core technology, and I was like, really, no, not really. we really need to study a lot more to I mean, we get the idea. Like, okay, we have the chain rule, and yeah, so you recursively apply the chain rule along your computation graph. You have the forward pass and the backward pass, right? So that's the one slide summary. Okay. Yeah, and then there is some notes about why modern frameworks, they will compute all this for you. So why even learn it? But he says it's good for it's good if you understand this, and I agree. Like for debugging and improving models, and then Karpathy also, Andrew Karpathy has a really nice blog on why you should understand backpropagation. He talks about backpropagation being a leaky abstraction. I don't know if anyone's read that blog and understands. See, I don't know what like leaky abstraction means, but
it is an example of why it doesn't always, or why there could be issues when you don't understand and you implement. He talks about a specific example of where there is a bug in somebody's code, and because of leaky abstraction, quote unquote.
I see. Okay. Okay, so that's everything that yeah, they talk about backpropagation here, and okay, they so then he shifts to like talking a little bit about regularization. So here we are we have a loss function, right? J of theta, and so regularization is used in many places. So you will have a L2 regularization or an L1 regularization. So in this case, he defines. So basically, what he does is take the square of. So the J is a function of theta. So say you have k values of. It's a vector. Say you have k parameters, right? So you take the square of each of them and sum it, and add that to your loss function. So one intuitive way of thinking about this is, if you're, let's say, this ensures your if your thetas become really large, like say 10,000 each or something, this J of theta will blow up, right? Because of this summation, you get a very large summation. So what this does is, you want to minimize the loss with and not allow your parameters to get too big. And I think lambda is it's also is it a hyperparameter? I'm not sure. Okay. Yeah, so he talks about you need this to prevent overfitting in our neural network models, and because otherwise you might just memorize your training data. So if you just have a simple 2-layer, 3-layer neural network, it will just the training. If you keep training, he talks about it will your training error will decrease a lot, and then when you run on a test error, you might not get the same performance. And he talks a little bit about that. Yeah, this is like overfitting and how you could prevent overfitting with using regularization. I'm on slide 50. If Joseph, yes. See, here, and another topic where, and this is one of the things I was talking to Srinivas also last week, is that this, like, some of the lecture material is just jumping around, right? We talked about back propagation. We had one slide on regularization where we could easily spend half an hour on regularization. And now we jump on vectorization, right? So just, so when you're looking through this, definitely look through 231N or even CS181. They go into each topic a little bit more. Here he talks about like if you if you use vectorization, you would perform much better, like in performance wise. And yeah, too long, did not read. Wait, this is awesome. Okay, wait. Yeah, so they're saying, so you especially in, like if you use MATLAB or Python or whatever you're using, if you have nested for loops, that really becomes very slow. So you try to avoid like nested for loops and try to do like just work with the vectors directly. I had when I was a TA for an image processing class. So one thing we did, we are doing a simple filtering operation, and instead of doing for loops, if you vectorize your code, it's just much faster. So in this general technique, not just for NLP, but also applies to a lot of image processing tasks.
Mehul, one question.
Yeah.
One question in this regard. So actually, I always wondered why it is the case. So for loop, definitely we all know that it is very cumbersome and all. So why does vectorization in computer programming work so well? Is not my understanding was that behind the scene it is again the for loops only. So definitely it is not like that. So,
yeah, I think you should read up on broadcasting, because so it's a technique that initially might be a little hard to understand, but what usually happens over here is instead of doing a for loop, what is happening is copies are created and they're multiplied. So, I mean, I'm a little unclear. I won't be able to explain broadcasting very well at the moment, but I think if you refer to any of Jeremy Howard's Fast AI courses, he's done a very good explanation of broadcasting.
Yeah, so if there are any computer scientists here, they might want to explain this, but
I will look it up.
What's going on underneath the hood is that the compilers are optimized to, modern compilers are optimized to do this kind of thing, making use of parallelization. So when you do a vectorized operation, you're doing many operations in parallel. For example, if you do a dot product, instead of calculating x1 times y1 plus x2 times y2 and so on, it's just bang, they do all the x times y's all at once, and then they do the whole addition.
So it's a combination of multiple techniques, some of which have been mentioned, like, for example, the fact that broadcasting is used, which is essentially, and you as the person suggested, you should really go look at it because it's fairly complex as to how it's done under a variety of conditions. But it's a combination of broadcasting and then compiler tricks that Joseph talked about. And then in the hardware, there are things which happen, for example, called SIMD, which is single instruction, multiple data. So when you multiply and use matrices, and that's one of the reasons eventually you got to GPUs, which can handle multiplication of matrices and large matrices in parallel very quickly, because all of them are done simultaneously. So it's a whole stack of techniques rather than just for loops. At each stage you optimize. So you optimize at the level of programming with things like broadcasting. You optimize at the level of compilers, as Joseph said, to structure the data in caches and other places. And then you also optimize at the hardware level to make the computation occur in parallel and therefore much faster.
Oh wow.
Okay. Oh.
That's awesome.
So would
Thank
it be fair to say that it's mostly parallelization, Srinivas?
Yes, combined with data storage optimizations at the compiler level, because you don't want to move the data in and out, which is another reason why sometimes GPUs suffer because they don't have as much memory. So mostly, but not all.
That's really helpful. Wow, I didn't know about the hardware stuff. And yeah, what Abhinav said, yeah, with the broadcasting, I remember now, like one of the Andrew NG lectures, he spends a lot of time explaining broadcasting. So if you, I think it's his new startup, the deeplearning.ai, and he has a series of five courses, right? And one of them, I think the first course or the second course has, like, he spends like like almost an entire lecture on broadcasting. So that should really help you. I should put a note on that. Okay, he talks about like because this lot of these what we talked about last time is you need a non-linearity. So the original was a sigmoid, right? So which was like which takes your input, say you have minus infinity, or you have you have minus infinity, and or you have plus infinity, right? So you can go, it squishes in the input from 0 to 1, right? Yeah. And when z is 0, it is 0.5. So that was the original nonlinear function that's used. And he talks a little bit about tan h, and I don't know the timing. Like I didn't know hard tan h till I saw this slide. This was familiar from previous times, and then and of course the more modern nonlinearity is the ReLU, and which is most of the times I've just used max, which is just simply a max of a max of z comma 0, and he talks about like a leaky ReLU, which is you have some parameterization, like instead of when x is less than 0, instead of just being 0, it's like a very small number. So it's like, how do you pick yet another parameter to pick, right? But so far in my practical, like I do like a lot of like say classification at work, and ReLU's been more than enough. I have never, like, maybe I should try leaky ReLU or one of these other parameters. Yeah, he talks about, like, he tries to make a note that like we want a non-linearity, right? That was the whole point, and it's still like, but on this side, it's on when z is greater than 0, it's a linear function, but it's just when it's less than 0. So he makes a note that he was amazed that this works really well. Talks a little bit about it, mentions that briefly in the lecture. Yeah, I sorry, I couldn't get through parameter initialization because I don't know if anyone else has experience with this. He's like, initially, so you say you have some biases and weight matrices, right? Like, so initially you could just assign random numbers to all your parameters, but there are some initialization techniques where the most popular one is called Xavier Initialization. And
yeah,
go ahead.
sorry, yeah. So I think this brings us back to like last year when the FastAI course was released, deep learning from the foundations, and like I would say, like the first lesson, there was a lot of focus on the importance of initialization, and the focus was basically on computer vision and the MNIST dataset, but there was a really good example of the different modes of initialization, and there were a lot of resources in the videos, side notes that you can use for knowing about initialization.
I see. Okay. Yeah, and so this is it kind of like this whole lecture, right? Like you have so many topics, right? So now we had parameter initialization where you could have an entire lecture, right? You had regularization where you could have entire lecture. So I feel like this is like he just like assumes like, okay, you know neural networks, and we are just going to do like a review, right? Or it's like, okay, this is these are some of the important things, and you can go and spend time figuring it out. I remember the lecture Abhinav mentioned. He was like Jeremy Howard spent a lot of time on that, and he found a problem in like the PyTorch parameter initialization. And there was a really nice thread on Twitter with Jeremy and Sumit, who's one of the PyTorch like founding creators. That how come why they had implemented the specific implementation of initialization in PyTorch, and I think they found a bug or something and they fixed
Yeah,
it.
I think that this section, parameter initialization, is really missing a punchline, and that is that, a TLDR, for so to speak, because what parameter initialization is meant to do is to prevent problems with the gradient that you can encounter when you have many layers in a network, and these problems are they're called vanishing gradients and exploding gradients. When the gradients, as they propagate through the network, they get smaller and smaller and smaller, so you're not learning anything, or they could get larger and larger and larger. And this prevents that from happening by holding the variance to be constant. It doesn't let it grow infinitely or shrink infinitely.
I see. Yeah, he mentions briefly. In wide details about gradients, examples in future lectures, exploding and vanishing gradients. But it's like you said, it's missing the connection, right? This should be connected to that initialization. But maybe one of the future lectures has a little more details on that. Non-linearities. Okay, I'm not going to go into this, but I couldn't cover optimizers is a whole class, right? This is and yeah, that's some of the practical advice. So there are many different optimizers you can use, and if you're just starting out, Adam is a good choice to begin with. But yeah, I don't remember the details of Adam. Okay. So I have a few more minutes. I want to share a few resources I found really helpful. So of course, the like we talked, the 231N slides are awesome. They have a TA section on backpropagation, which is great too. There is so basically, in summary, right, there are these three CS classes: 231N, 224N, 131, and there's another one which is Andrew Ng's original class, which was CS229. So this TA did an awesome job. What he did is he started making these incredible cheat sheets on machine learning, and he put them on GitHub. Okay, so I'm just sharing the neural network one. So you have the basic architecture. So if you want like a quick refresher, and he just calls them as cheat sheets too, is okay. You have okay, that's the equation at each how you do each computation, the different possible activation functions, the sigmoid ReLU and the leaky ReLU that we just briefly talked about. What is your loss function? And of course, the key part about backpropagation. And basically the recipe, right? So if you were to write this on your own, you actually just need these 4 steps. You take a batch of training data, we perform the forward pass, backpropagate, compute the losses, backpropagate and get the gradients, and then update the weights of the network using this equation. So I thought this resource was really nice. And then because now you have the entire summary, right? Like you have this 1-page summary, and you can dive into each topic given in this summary, and giving how much time you have. Okay, so they similarly, like last week we talked a little bit. I didn't find it last week, so we talked a little bit about supervised learning, right? I thought this was awesome because like I was showing the decision boundaries last time, and so similarly he's showing the decision boundaries, and he talks about he summarizes models as discriminative models and generative models. That was I had not seen that before, and this. Yeah, I think we briefly touched. You have two types, right? Like in your supervised learning, you either have like a regression, so you're predicting a house price or a stock price, right? So your outcome is continuous, or you predict some class, right? And okay, I don't know where the NLP fits in, but yeah, you could say like the document, like the sentiment, right? Maybe that's the example we saw was the class example. So this was. Else I want to see. Yeah, this was great. And did I miss anything? Let me see. I wanted to. Yeah, these were so he has this entire set of cheat sheets. They're all meant for 229. I haven't looked. I couldn't find the lecture material for that. Maybe I just ran out of time. Yeah, and if you want to go from I definitely recommend this the recordings from our session with Joseph, where matrix calculus you need for deep learning. I have the YouTube playlist link here, and I think that's also great to dive into more detail. And if you are like me and you want to go back, you forgot some of your multivariable calculus. This series from Khan Academy is awesome. It's like every single thing I think it's 26 videos. I was like, okay, no, I didn't go through all of them. Yeah, I just started looking at, but they have stuff like directional derivatives and gradient at, why is the gradient in the direction of the steepest ascent? You can spend like weeks going through all this material. Yeah. What else did I want to? Yeah, and this, and so this video is. Oops, maybe before I pushed it. Yeah. Okay. So these Khan Academy videos on multivariable calculus and the 3 blue-brown videos are by the same person. He's really good at explaining. Okay, I'm out of time, but thank you, and thank you for all the inputs. It really helped the discussion.
Mehul, you've gone over and above what you needed to do. You did a terrific job today. You did full justice to this lecture, I think, and especially putting together all of the nice references and so on that people can use to dig into it. So, if you could post this thing that you just showed us on the Slack group, that would be terrific.
Okay.
And I just really want to thank you for doing such a great job.
Thank you, Joseph. Yeah, and this is a Git repo, so you can fork it or it's a public Git repo. Yeah. Okay. I'll post it on Slack. Stanford. Yeah. That's my. Do you want me to post the PDFs? Some of the good PDFs.
Sure.
Yeah. Okay.
Yeah, sure. That would be great.
Okay.
Yeah, Mehul, just could you also post the presentation, the 40-page presentation that was there on propagation?
Yep.
Yeah, thanks. That was a really good resource.
Okay.